Welcome back to this conference brought to you by the 4 UK Agri-tech centres. And now we're going to hear from them, starting with Dr. Harry Langford. He's Innovation Network Lead at CHAP. Dr. Langford is going to talk to us about climate change and Agri-tech's role in improving the resilience of the food system by moving the sector closer to net zero.
Thank you all for logging in for this event. I'm Harry, the Innovation Network Lead at CHAP. And I'd like to talk to you today about agriculture and a climate resilient food system. Over the next 20 minutes or so, I'm going to provide my perspective on this challenge, give some examples of where the Agri-tech centres are helping, and provide a bit of a forward look as to what we need to prioritise. Some brief background first. As you can see from the figure, the global food system contributes around 20 to 30% of total greenhouse gas emissions. But these aren't equally shared across the food system, with more typically attributable to production, so pre-farm gate, than the rest of the food system. Within the UK, we perform slightly better, but once the embodied emissions of our imported produce are accounted for, the food system still contributes around 19% of greenhouse gas emissions. However, it's obviously not that simple, because the food system nourishes our global population and provides employment for around 1.3 billion people. So we must balance these factors when intervening. You can see from the pie chart that agricultural production contributes around 45% to the UK's food system emissions, and that makes it an obvious target for intervention. But the other 55% of the food system has an equally important role to play, an example being the reduction of food waste, which I'll talk to you later. Focusing a little more on the challenges and opportunities, building climate resilience within our food system has been estimated by studies such as the UNEP one highlighted to be capable of delivering significant emissions reductions on the order of around 20%. And it's exciting to see these positive estimates. We understand that a more resilient food system can better respond to stresses and shocks, combining the development of more robust soils and crops with less waste and more circularity. Better optimization of the interfaces between the food system and the natural environment is going to be key in delivering change at the rate needed. Focusing a little more on agricultural production, which can't eliminate its emissions entirely, as illustrated by the scenario lines in the top figure. The critical challenge is to maintain a suitable balance between food production and emissions mitigation. This challenge is compounded by the need to begin to future-proof our production system for a changing climate, and by discrete events such as extreme weather and other barriers to transition. But the key opportunity here has to be that plants and soils, the foundations of our production, are carbon sinks. There are pathways to a higher attainable organic carbon content in soils, and both sequestration and technological improvement have as fundamental a role to play in emissions reductions as offsetting, in my opinion. Over the next few slides, I'm going to talk through some different production and technological perspectives on this to try and exemplify how agricultural production can build climate resilience and reduce net emissions. I'm starting here with the crop production system. And here I think that a number of pathways need to be explored, as summarized. The fundamental objectives should be to increase the robustness of practice, plants and soil, and to improve decision making. I want to focus in on a couple of contrasting ways, so building soil health and embracing controlled environment agriculture, or CEA. When I talk about building soil health, I don't just mean disturbing it less and leaving a living root or crop residue. I mean enhancing root systems through breeding, building improved mycorrhizal fungal networks around those roots, as in the figure on the left, increasing the amount of exudates released and enhancing both soil structure and the soil biome. Conversely, CEA typically doesn't grow in the soil at all, and so provides a different opportunity. The opportunity really is to relieve pressure on our agricultural soils to allow for more carbon sequestration, but also to align with other industries and capture and use carbon from biomass power stations or heat from water treatment works, for biomass production. Turning next to the animal production system. CIEL have handily just released a report on this, and the key messages from that report are that A, precision approaches both to grass or forage production and to livestock management and breeding have the ability to improve decision making, reduce inputs, and boost outcomes. These can not only improve system resilience, but also allow that extra cut of silage, for example, that can boost profitability. B, building resilience and sequestration into grazing pasture is going to be critical here. Simply alleviating compaction could provide substantial benefits to resilience and net emissions, but furthering this through landscape diversification and mixed swards, including legumes, will further those benefits still. And finally, novel feeds and feed additives are an important part of the jigsaw, as replacing imported soya needs to be a top priority. Insect proteins are currently being explored as animal feed, and seaweed and its derivatives are helping to optimize the gut microbiome and reduce methane emissions. So the 4 centres have ongoing and just starting projects that are trying to take us further down this road. And 2 examples related to the crop and animal production spheres would be the use of CHAP's precision tillage equipment on 2 EU projects to improve our understanding of the practical challenges of implementing companion cropping and its potential for improving resilience to disease and for lowering fertilizer inputs. And the second being the Dutchy Future Farm, supported by CIEL, which takes a unique approach to farming system optimization across 3 comparative herds, aiming to optimize for welfare, productivity, and reduce greenhouse gas emissions. And just to say that all of these case studies are available in more detail on the 4 centres website, by the way. So focusing a little more on agri-tech now, specifically, there are obviously a large number of ways in which technology already does and can support improvements in the climate resilience of our food system. I can't cover them all in this short talk, but I did want to talk to this, so I've highlighted 4 principal areas in which I think agri-tech can help the most. For example, the circular food system in the top figure indicates that the main ways to improve efficiency, resilience, and net emissions are by preventing overproduction and overconsumption, and by minimizing and recycling inputs wherever possible. To this point, I think that waste to worth is going to be a critical area of research and development going forward, closing resource loops and contributing to system resilience. The lower image indicates prediction, which is another area that I think will be critical. Because of the risks involved in food production, preventative treatments of pesticides, for example, are still often used to ensure a profitable yield. If we can identify health or disease problems earlier, alternative treatments open up to us that can hopefully build efficiency and resilience back into these systems by tackling antibiotic, pesticide, and herbicide resistance. So in terms of developing agri-tech solutions, I'd like to overview another couple of case studies here. The first, the Hands-Free Farm project, supported by Agri-EPI, is looking to explore automation in order to improve the efficiency of farming, to tackle key challenges such as compaction, and to reduce input costs in order to improve system resilience and lower emissions. And secondly, the Gelponics project, on which CHAP is partnering, which is looking to develop a novel and recyclable hydrogel growing media developed by AEH Limited into a sustainable and efficient controlled environment production system. Existing growing media such as rock wool and peat have significant carbon footprints, and peat use will soon be banned. So work in this area is critical to the future sustainability of CEA. Widening the lens to the rest of the food system, I think that 4 ways in which the agri-tech centres can help are around tackling food loss and waste, improving measurement and accounting, and increasing knowledge and whole system understanding. Food waste, perhaps not easy to visualize until you see infographics like this one from WRAP, actually accounts for around 3% of the UK's domestic greenhouse gas emissions. So better forecasting across the food system to predict demand and tackle gluts and shortages could play a significant role in tackling some of this. In terms of measurement and accounting, better inventory taking of greenhouse gas emissions and carbon stores can not only allow us to better account for the emissions within the food system, but also to identify better interventions and even make carbon investable. You can see from the World Bank data in the bottom image that the agricultural carbon market is immature compared with others, but it has the potential to de-risk and fund the fundamental production system changes that will be necessary to meet carbon net zero by 2050. And so this must be a focus of our attention. Across the wider food system, the Agri-tech centres are focusing on post-harvest losses and improving data platforms to support climate resilience and mitigate emissions. The CROVER project, which Agri-EPI partner on, will develop a robotic solution to stored grain sampling for better assessing the spatial variability in grain quality and to detect conditions that might lead to pest and disease problems earlier, thus protecting our harvests better. The work of Agrimetrics in improving data interoperability and building a digital platform for farming and the food system has extended further towards carbon sequestration and resilience with their partnership on the Regen Agri platform, which aims to better quantify the positive changes that farmers are making and link this ultimately to accreditation and reward. And so to try and summarize the perspectives I've offered and look forward as to the critical priorities, I'd like to draw upon the Food and Land Use Coalition's infographic, which nicely shows the need for diverse yet connected action across all food system actors to truly transform the food system. With this in mind, when I think of agricultural production and the food system, I feel that diversification must be the focus of a climate resilient food system. And by this, I mean a greater diversity of food grown, varieties or species used, processes creating value from residual biomass and recirculating it, supply chains localizing food and improving choice, and diet for the benefit of human health. And I also think that sustainable nutrition must be the priority. And here I mean better alignment between sustainable inputs, such as circular nutrients and renewable energy, with outputs such as freshness and fortification that are desirable. And agri-technology will play a critical role in enabling this improved practice and supporting new farming systems. Thank you for your attention, and I'll leave you with a question that I hope really cuts to the core of this, which is, how can primary producers make the move to net zero and benefit their bottom line by improving the resilience of their food and farm system? We'd like to think that some of the work that the Agri-tech centres are currently doing will help to answer this question. And if I've sparked an idea that you'd like to discuss further in this area, please feel free to get in touch with us. Thank you.
Dr. Harry Langford from CHAP. We're now going to hear from Agri-EPI in the shape of their Chief Technical Officer, Dr. Shamal Mohammed. Dr. Mohammed is going to talk about sustainable productivity, in particular techniques which have the potential to improve both the precision and the efficiency of key agricultural management and food production practices.
Good afternoon, everyone. I'm Shamal Mohammed. I'm a Chief Technical Officer from Agri-EPI Center. And in my session, I'm going to be looking at the sustainable productivity. One of the key challenges for us is basically producing more food in a more sustainable way. And in terms of the productivity, there is a demand for increasing food production because of the increase in population growth, as well as the demand for more energy and more greener energy as well. So there is only two options. Either we can intensify the agriculture system, the existing one we have right now, or we need to expand our agriculture activities. So in terms of agriculture intensification, there's also some environmental impact like soil degradation, greenhouse gas emission, but also if we expanded the agriculture activity, there is also an impact on the biodiversity losses and deforestation, for example. In the same time, when we expand in the agriculture, there is also an increasing demand for more land for options for bioenergy and carbon capture and storage, like tree, for example. So there is almost a dilemma, if you like, and it's a vicious circle. So you increase productivity, but also you need to think about the sustainability and also the impact of biodiversity losses, deforestation, soil degradation on how these can impact on the productivity itself as well as the whole impact of climate change and the challenges facing the industry. But this is only on a primary production side, but there are wide range of other issues around food production systems, like food waste, nutrition and dietary requirement, the human health, the whole consumer's behavior and the demand and preference as well as the very complex food supply chain. So these are the key challenges in terms of sustainable productivity. In terms of the technology's role, what the technology can do is, in my view, I just put it in three different areas, if you like. So the technology can help us to make the system, the food production system, more efficient by minimizing the waste and utilizing and optimizing the input application, but also can help us to diversify the food production system, for example, mixed farming, or looking at the whole concept of circular economy and reusing the byproduct of food production system again into a different system. We also, technology can help us to build and develop a more integrated system where we can look at the whole production as well as sustainability on a more comprehensive way, on a landscape scale or a national scale or even an international scale. And also, if you look at it in a sort of a supply chain, linking what actually is going on the farm scale into the whole food processing system as well. So there are three main roles for technology to make the system more efficient, more diverse, as well as more integrated. And that's really is the in the heart of the sort of the sustainability, and this is where the Agri-tech centers building this capability to help the industry to move toward more sustainable productive system. And the building block, in my view, for any sustainable productive system is improving our soil health, and this is exactly what CHAP is doing by building this capability for the UK Agri-tech sector. This is more important because improving soil health using different agronomic option instead of using fossil fuel and increasing the impact on the environment, optimizing the crop growth and improving soil health using the plant root is one way to overcome these challenges for productivity. And cover crops shows that really can help improve soil health and minimize the soil cover, the risk of erosion, minimize the water pollutions, as well as maintain and increase the organic matter. So the facilities at Soil Health from CHAP is providing this capability to the UK Agri-tech sector by bringing a world-class glass house with sort of a lysimeters where we can look at the function of different soil, but also looking at the impact of different cover crops on the structure as well as on the aggregate in the soil stability and soil porosity as well. So the root can be assessed and look at a different mixture of cover crop for specific type of crop as type of soil as well. So this facilities has been working in this area for a while, and they provided really interesting outcome to look at how the root improves soil, but also can look at the different practices to provide a better soil structure that can resist soil erosion as well. Root can also improve soil infiltration rate, and also this is quite important for minimizing the runoff as well. So there is not only is important soil health for crop production, but also for minimizing other environmental impact like flooding as well as water pollution as well. So the root screening in this project at CHAP facility is being done for 7 cover crops, and they looked at a different experiment in these big containers and looking at a different soil type like sandy clay loam, as well as at a different structure condition, as well as different wetness level to see which cover crop have a better improvement in soil structure as well as soil health. And that's the kind of facilities that the CHAP, as well as in collaboration with Cranfield University and also Agri-EPI, we have a gantry where we can look at a different canopy changes depending on soil as well as different treatments. So this is really interesting and a world-class facility for doing any work in soil and soil health. So moving from soil into a water, because I think we talked about healthy soil and healthy crop, but obviously water is a crucial part of this production system. So in order to get a healthy crop, we need to have a better understanding of the water balance. And this is exactly what Agrimetrics is developing an analytic suite in collaboration with Airbus, and that's all based on a wide range of data set for millions of data points, and looking at how this data can be modeled in order to develop a water balance for a specific field, so the farmers and growers can get a better understanding on the level of water availability. So this is just an example of a grass field for the whole season. You can see the graph in the middle. This is basically the rainfall, daily rainfall, as well as potential evapotranspiration. And based on that 2 factors, you can model your water availability in the soil. That's your water balance on the top. But also, because they're using multiple satellite data, they can look at leaf area index, for example. So that's where you can see the grass is kind of dying down and then growing up again until August, July, August time, when you have a less biomass in the grass, but you have more crop water stress. And this is the kind of technology can help farmers make better decision on the water availability, but more importantly, for predicting the biomass for the crop, and in this case for the grass. So this example takes you through a year of life of a grass field, and using the leaf area index to show the grass growth larger from the winter through to the summer until decline rapidly in the mid to late summer. The decline is also kind of coincides with the extended period of about a month or a half, which the rain is very low. The data implies that when the field dries out, the grass crop experiences was stress and begins to die back. Once the rain returns in the autumn, the grass recovers. So that's sort of the model that can predict and develop a tool for farmers to manage the grassland, as well as in case of crop. This information and this tool can be used for scheduling irrigation and maximizing the utilization of water resources, which is an important part of sustainable productivity. Just on while we are on the grass, and I think this is quite important, and in Agri-EPI Center, we looked at the precision grazing in more detail at our Southwest Development Dairy Center. This is where we looked at different options for mapping the biomass of grass at the field scale, and also even the variability within the field. And why is this important? Because basically the cost of production is the key for farmers. So if you are grazing your dairy cow, a litre of milk is going to cost you around 3 pence per litre. If you're using a silage, it's around 7p per litre, while using a concentrated feed, the cost of production will go up to 14p per litre. So maximizing the grazed grass is quite important economically, but more importantly, this is the type of resources is not being utilized more efficiently. So technology can help us to bring that utilization, that resource into a better utilization for farmers and the growers. Why is important measuring the biomass for grazing? Because as I said, it's depend on how much dry matter is available and how the farmers is measuring this biomass at the moment is using raising plate meter, which is quite time-consuming process. So farmers need to walk the whole field, or sometimes using a visual assessment for estimating how much dry matter available in a specific field and in a specific area. So in Agri-EPI last year, we were partners with Cisco at our Southwest Dairy Development Center. And one of the use cases for the new technology like 5G was to look at the measurement of biomass of grass. So we used this very special drones with a 5G enabled capability to map out the biomass of the field on a daily basis. And based on the information from the image we collected, we can extract and build a model that can nicely correlate it with the biomass. And building that kind of tool for farmers will help them hugely to utilize this this important resources in dairy production system. So this was basically a sort of a follow-up from a previous project which we used the satellite data exactly for looking at this this aspect of grassland management. So that was another project we've been involved a few years ago with Cranfield University and Satellite Application Catapult. We looked at the application of satellite imagery instead of 5G and drone, basically. And also, this has also provided a very interesting outcome as part of this project. So the grass is important on a field scale, but also on a national scale as well. And this is where colleagues from CIEL, they work in collaboration with Agri-Food and Bioscience Institute in Northern Ireland to develop a national capability for grass check for the whole of UK. And that is, it will provide a more national changes in the grass growth as well as dry matter availability, and it's been supported and funded by AHDB, QMS and HCC as well, and CIEL is working with the researchers at FB as well and Rothamsted to develop this tool for the whole farmers across United Kingdom. As part of this service, 50 locations across the UK is being selected, and the farmers actually providing data for this model to provide a better understanding about the grass growth across the whole UK. And the farmers, as part of this service, will get a weather station, automatic weather station, soil moisture and temperature probe, and looking at the electronic plate meter, animal weighing platform, and access to AgriNet annual subscription, but also to do the grass analysis on a fortnightly basis, other farm informations. So all these data goes into a model in order to provide this national understanding of grass growth and dry matter availability for all the dairy and beef farmers across the UK. So this is the type of output the farmers can get. So this is from March to November, and you can see there is a grass growth for the dairy farm as well as beef and sheep farmers, and the dotted line is the average from the last year. So farmers can get a sort of a grass check summary table for specific weeks. So this is for the week beginning of 19th of October, and it will separate it into a different region, North England, Scotland, South England, Wales, and also you have an average, and then it will provide information about grass quality like dry matter, crude protein, as well as sugar. So farmers can see what actually is happening in terms of the grass quality in those regions. So you can also get a sort of a more specific regional-based data set, and it will compare it to the last year as well. So farmers, if they are in the north of England, so they can see where they are compared to the average farmers in that region, as well as compared to the last year. So it's the same thing for south of England as well as Wales and Scotland. So this is the kind of projects and activities that the Agri-tech centers, all 4 centers, are investing in the industry to help farmers, as well as the innovation, and then bringing the innovation and technologies to solve these problems for the farming industry. And I think the key message is for us to move from that linear model of take it, make it, and waste it. We are more now looking at the sort of a sustainable productive system, which is more secular in terms of productivity, and technology can play a huge role in enabling that transition to moving the industry toward more productivity, but also sustainability in the same time, by increasing the monitoring as well as decision-making power, as we demonstrated in this, for example, from 4 centers of Agri-tech, but also looking at the visualization, the transparency, and more importantly, the feedback-driven intelligence, where farmers, supply chain, as well as consumers can feed back into the chain, and then in order to improve efficiency, diversity, as well as the integration of the whole system. So I'll stop here, and I'm happy to take any questions later on. Thank you so much for listening. Thanks.
Dr. Shamal Mohammed from Agri-EPI. Well, now let's hear from Anna Woodley, Head of Sales and Marketing at Agrimetrics. She's going to talk about crop and livestock health and how digital twins may be an answer to reducing risk in an increasingly complex food system.
A highly topical challenge to our food system is the impact of disease on our ability to sustainably deliver safe, healthy food to our population. Whilst the food system arguably responded well to the COVID challenge, this may not be true of all of the risks that the system faces in this space. For example, many of the methods that we've previously relied on to control pest and disease are being lost. Resistance to pesticides and herbicides is a major contributing factor. Recent studies out of Rothamsted Research provide evidence of reduced sensitivity of blackgrass to glyphosates. And in the veg sector, resistance of blackback diamond moth to pyrethroids continues to be a major challenge. In 2018, the World Health Organization declared that antimicrobial resistance is one of the top 10 global public health threats facing humanity. as well as being considered as one of the largest costs to the global economy. At a global scale, emergent risks such as African swine fever and fall armyworm pose significant threat to our supply chains. Dysfunctional food systems are contributing to soaring levels of malnutrition. In 2019, it was estimated that 1.9 billion of the global population were overweight or obese, and over 500 million were underweight or suffering from wasting diseases. The One Health concept emphasises that pathogens affecting humans and animals are part of the same ecosystem. Therefore, managing risks in one species cannot be separated from another. This concept can be broadened to recognise that everything we do takes place in the same ecosystem. For example, soils cannot be managed separately to crops, ecosystem services are interdependent, carbon sequestration cannot be separated from food production. And environments that are conducive to rising levels of obesity are the product of a food system in which food consumption and food production are increasingly separated. The risk posed by these challenges is radically amplified by their interdependence. Our food system is unfathomably complex. Actions can have far-reaching and unforeseen effects. For example, few foresaw the Arab Spring when poor harvests led to rising grain prices in 2010. But the greatest risks to an interconnected food system stem not from the unintended consequences of isolated management decisions, but from many loosely connected actions compounding to threaten systemic crash. The collapse of two relatively small US banks catalysed a chain of events that produced the worst global recession since the Great Depression. Our food system is similarly exposed. It's so complex and therefore it's unpredictable and inherently vulnerable. We can begin to tackle the challenges associated with these complexities by taking a systems viewpoint. Systems thinking is an approach to problem solving that considers an overall system and its linkages instead of focusing in silos. It's this approach that's been adopted by the Centers for Disease Control and Prevention in the US in their work on the H1N1 swine flu virus and other associated G4 viruses. This enabled researchers to successfully manage their threat to humans. Similarly, a recent article in The Lancet suggests system thinking can help policymakers understand and influence the spread of infection and the multifaceted consequences of COVID-19. And this is because society is a complex adaptive system, very much like our food system. Taking a systems view, pest and disease risk needs to be managed beyond the farm gate. For example, predictions of pest outbreak can be moderated by considering previous and planned interventions at a scale larger than the farm. Antimicrobial resistance can be managed by targeted use and balancing differential disease risk and treatments across species. And human nutrition should be considered a farm-to-fork challenge. We cannot separate how food is produced from how it's consumed. As an industry, we're seeing more and more businesses embracing emerging technologies such as predictive modelling, AI, and blockchain, with a real focus on tackling the challenges associated with disease and health. There seems to be an insurgent rise in large corporations taking serious action around One Health. Microsoft's AI for Good program, for example, supports early-stage startups specifically focusing on in this space. But by its very nature, systems approach requires thinking to extend beyond the boundaries of individual consumers or businesses or countries. A joined-up or connected approach is essential. And it was this requirement that drove the creation of the 4 Centres for Agricultural Innovation and that motivated Agrimetrics to build the sector's most advanced linked data marketplace. The 4 centres are beginning to tackle some of the challenges associated with disease and health, and each are adopting a systems viewpoint when developing their research and solutions. Crop Monitor Pro is a state-of-the-art pest and disease decision support platform Created by the Centre for Crop Health and Protection in association with FERA, the tool provides information sourced from monitoring sites located across the country and reports up-to-date measurements of crop pest and disease activity in arable crops throughout the UK. Samples collected from these monitoring sites are also used for analysis and research by other services within CHAP, for example, the National Reference Collection and Molecular Diagnostics Laboratory. Monitoring of pathogen pressure prior to the development of disease symptoms is one example of the services which Crop Monitor Pro delivers. Co-deployment of spore traps at each of the monitoring locations collects samples for lab analysis of spore release and dispersal in relation to weather factors. These spore traps carry out an automated DNA test, which along with the spore count is sent to the data platform. The solution uses in-field diagnostic services to detect latent infection in crops prior to symptoms appearing. And the potential for in-field detection of pesticide resistance is due to be incorporated in the near future. And data from Crop Monitor Pro is soon going to be made available via the Agrimetrics data marketplace. The Centre for Innovation in Livestock has supported a UK-China consortium to secure vital funding to develop a new non-antibiotic antimicrobial treatment that could control the spread and development of antibiotic-resistant pathogens in poultry. The technology couples a cancer medicine delivery system called microparticles with reactive, short-lived antiseptic compounds. And lab trials have already shown the loaded microparticles to be effective in treating antibiotic-resistant bacteria. The novel technology can be customised to meet the specific needs of the end user, delivering a toxic payload to bacteria present within the animal and can be produced cheaply and safely. The use of antimicrobial treatments in agriculture is vital in protecting animal health and aiding in the production of safe and nutritious food. However, overuse of antibiotics in the livestock sector is attributed to the rise in MDR bacteria, constituting a significant threat to broader animal and public health. This is especially a problem in China, where antibiotics are still used for growth promotion in livestock. Early trials are being carried out in CIEL and Shruck's Alimure Avian Innovation Skills Centre near Edinburgh, and the initial findings will be subsequently trialled across several commercial poultry farms in China. A collaboration bid between Agri-EPI and AQUALIFE has received funding from the Seafood Innovation Fund. Awarded by the Centre for Environment, Fisheries and Aquaculture Science to develop and launch a transformational fish vaccinating robot by the end of next year. The robot, named INCUBOT 2, will be able to vaccinate fish at sizes below 20 grams as opposed to the common weight of between 30 and 120 grams. And this allows producers to increase productivity by growing their fish out of the hatcheries far sooner. The robot will be capable of vaccinating most species of farmed fish in very large numbers. And INCUBOT 2 will be a mobile platform which allows AQUALIFE to offer automated vaccination to smaller fish farms which otherwise couldn't afford to invest in large scale in mobile systems. The robot will also help to improve fish quality using artificial intelligence and deep learning algorithms to increase vaccination accuracy and improve fish grading. And additional image processing algorithms are being developed for new species, as well as uniquely individual end-of-arm tools to grip the different species of fish. The end-of-arm tools will be designed to achieve the least handling possible of each fish, which will improve fish welfare and also means that growth performance will be more efficient post-vaccination. As we've seen, there is much that's already being done by the centres to tackle the challenges we face in the area of disease and health. Much is being done by businesses and universities and research institutes beyond the centres as well. The challenge that we now face is to connect these initiatives to enable systems thinking, and a digital twin may well be the solution. Digital twins are attracting a lot of attention, but providing a digital twin for a system as complex as the food system is incredibly hard. In engineering, a digital twin is an exact digital copy of a machine. And this enables users to simulate the impact of management actions without risking the physical counterpart. Or they can predict the future performance of the machine based on current and recent performance data from the digital twin. It's this technology that enabled the rise of predictive maintenance, which has reduced maintenance costs in leading factories by almost half. The closest analogue to a digital twin of the food system are climate systems models, where the core is a well understood set of physical processes. The ecosystem which underpins our food system is much more complicated, and it's certainly less well understood than the climate system. A realistic goal for a digital twin of the food system is to establish a digital characterization of the current state of the system through using data. This then provides the basis for carrying out analyses and simulations on parts of the system and which focus on specific questions and challenges. As an example, a comprehensive record of cropping history combined with spraying records and pest prediction models begins to provide the basis of a digital twin to support landscape-scale pest predictions. The 4 centres provide the foundation for this vision. We have 3 centres covering the breadth of biophysical activity connected by a virtual data infrastructure. This provides the foundation for connected experimentation across, for example, plant, human, and animal domains. But more is needed. We need to provide access to the data that represents the current state of the physical system, not just an experimental version of it. And this is why we believe that a data marketplace is so important. It forms the foundation of an ecosystem in which data can be gathered, but more importantly, in which the benefits of managing at a system level can be transferred back to the providers of these data. Thank you.
Anna Woodley from Agrimetrics. Well, now let's hear from Stuart Blythe. He's Head of Business Development at CIEL. He's going to discuss food quality and provenance, including nutrient value, precision agriculture and livestock, and how to improve supply chains and reduce waste.
Good afternoon. I'm Stuart Blythe, the Head of Business Development for CIEL, and I'm delighted to represent the 4 centres on this subject today. I'll spend the next 20 minutes talking to you about the impact innovation and technology can have in supporting provenance and quality in a resilient food system. I will discuss some of the challenges and opportunities facing us and give some examples of programmes or capabilities across the 4 centres which are helping drive change across the food sector. So what does provenance and quality in a resilient food system mean? Well, let's begin with food quality. This is really healthy food that's enjoyable for people to eat. It needs to be nutritious. So this is food that supplies the nutrients that animals and consumers need and provides us all with the good calories that we require. It needs to be safe, so free from pathogens, chemical toxicity, agricultural chemicals, or anything that can result in a negative health impact. But also in terms of safety, we need to know and understand shelf life and maximise this where possible to minimise waste. We also need to think of the sensory experience. Good eating quality means we have something that we really enjoy and we savour. And also consistency is critical. We all have a real expectation of quality nowadays, and we know very well that all it takes is one poor experience to taint the perception of quality for a long period in the future. When we think of provenance, this is really food produced in ways that we accept or we expect. When we think about ethics in production, well, this means different things for different groups. But I have to say that common across most groups is that we're thinking about good animal health and good welfare and good consideration to minimising environmental impact for all of our food. Within origin and authenticity, it's absolutely critical that increasingly we want to know where our food has come from and that we can be confident that it is what we expect it to be. And this leads on to our ability to audit and trace food throughout our supply chains, which is absolutely essential to ensure confidence in practices and adherence to laws and regulations. And this is actually something that we already trust and take for granted. So a resilient food system really is food for everyone all the time. It's affordable and available food for everyone across society. It leads to diversified product lines and sources of supplies. It requires adaptable production systems, particularly in the face of environmental variations. And we know that we're moving into an era of climate change. We need to approach production with circularity in mind to drive less waste and unnecessary pressure on the supply chain. And we want producers really to be connected to the final market, to understand the impact and benefit of the choices they make, and be able to bring strong and quick agility to respond to changes in the supply chain. I actually want to quote the National Food Strategy at this stage, and it actually says that they aim to deliver confidence in a safe, nutritious, sustainable, ethical and resilient food supply chain for the UK, and afford the best farmers and food producers international competitiveness in an environment when the UK stands alone from the EU. So how do we start to look at some of the key challenges and opportunities for these different areas? Let's start with nutrient value. For our crops, we're wanting to maximise the potential as much as possible and harness new technologies to boost the nutritional value of our crops and improve freshness and shelf life. Three great examples of this are natural light growing. Here we're looking at the full spectrum light, and we know this allows plants to produce chemicals that affect the flavour, the aroma, the colour, and improve hardiness and shelf life. And I've got a great example of this to share with you later. New LED wavelengths. In a similar way, for indoor systems, these tailored LEDs have tremendous potential to design optimal crop lighting systems, maximise quality, taste and performance of the crop. Novel biostimulants. Here, a great example could be microbial biostimulants, which enhance plant growth and disease reduction. When it comes to the nutrient value of our meat proteins, well, here we really need to understand the nutrient value of proteins in the human diet itself. Relating this to both overall quality and environmental impact, we can start to define how much of each protein is required for a healthy diet and how much they need to be combined with other nutrients to enhance uptake. We also need to consider development of new and alternate proteins. And this is where we're supplementing existing feeds with things like insects, algae, seaweed. And these offer opportunities not only to diversify the nutrient supply chain, but also to complement our existing systems for the future. When we move to food quality, we need to link taste and eating experience with production parameters and really inform the whole of the supply chain in order to produce consistent, high quality food, leading to less wastage. For provenance, we need to consider opportunities beyond telling the consumer that their steak has come from an animal that led a contented, natural, happy life. We know that meat eating quality is already directly linked to the breed and to the feeding. And there are fantastic opportunities now to develop scanning technology and link eating quality to animal lifetime performance. The farmers themselves can receive clear market signals for the performance of their product and obtain a much fairer share of value by linking provenance through to taste and quality. In food safety, we can harness controlled environmental agriculture and produce crops in highly controlled conditions to maximize yield and drive clean, green growth products. We have new treatments, for example, phages or low temperature plasma, which can remove bacteria from food and can treat animals and further reduce the potential for AMR through the supply chain. There's also the potential for implementation of new sensor technology. A fantastic example of this is paper-based electrical gas sensors, which are being developed at Imperial College and can detect spoilage and relate this directly to the consumer through their smartphone. When we move on to supply chain and waste, these are of course critical to any resilient food system, and there are some key elements that drive resilience and quality. Creating links across the supply chain. Here, we can use the latest visual and spectral analysis plus artificial intelligence to accurately measure food quality and link through to consumer preferences, creating an opportunity to develop quality and consistency at the production stage. We can link and combine data across the supply chain, and this is absolutely essential to understand the complex interactions between what we produce and what the final consumer chooses. We don't necessarily need blockchain unless we're talking about data immutability, but we do need the capability to combine and translate multiple data sets together. When we think about agile supply chains, agility and flexibility is really key in future resilience, as is evidenced already in COVID responses. And this can be supported by local food systems, thereby diversifying supply routes and supplying locally or Great British produced produce and proteins. When we think about diversified UK crop production, this is really thinking about not putting all of our eggs in one basket and really having a range of local crops, efficiently grown with the support of new technologies. Increasing efficiency in meat production in the UK, we can do through continued development of quality, optimizing our feed systems and genetics, and further focusing on disease reduction. When we come to data sharing, this is more than just linking data together. This is active sharing of data. It's really needed to ensure that the value is secured for all parties in transactions across the supply chain. But being able to share data sets and build insights from multiple sources can bring large and rapid developments in understanding and really transform the approach across the supply chain. And lastly, and often most critically, we have food waste. New technologies to reduce waste in the supply chain, coupled with better prediction tools, are really now allowing disruption to be mitigated and an agile change to be possible, resulting in less waste. Developments also in food storage to try to keep food in an optimal state for longer also eliminates waste in this system. And again, we've got a great example of this coming up. So ultimately, all of these challenges and opportunities come round to focusing on precision agriculture and precision livestock. To truly achieve consistency in performance and quality, plus a lower environmental impact, we need increased monitoring, increased understanding, and increased control. This then becomes a continuous improvement loop. New insights are always driving new innovations, which in turn create change across the supply chain. This creates an innovation-focused mindset, which is always looking forward to the next opportunity. So I would like to try to bring some of this to life with some examples of where work from the 4 centres and the partners are supporting this development of quality and provenance across the whole of the supply chain. We'll take a look at some of the innovations, capabilities and potential technologies applicable to pre-farm gate production, all the way through processing and onwards through to retail and food services and ultimately to the consumer. I'm only going to give a flavour at the moment of what is possible, but in all cases, if you want more information, please come back to the centres for more detail. So let me begin at the start of the supply chain with the Natural Light Growing Centre. At this centre, through the cost-effective replacement of glass with ethylene tetrafluoroethylene, which is a material which allows full UV penetration, the impact of full spectrum natural light on crops with a protective environment can be studied. The centre has heating, irrigation, environment and electronic control, that keeps it operating at maximum efficiency and allows really detailed control studies to be carried out on a number of impact areas. And this can lead to studies on plant health, nutrition, flavour, shelf life, growth and development, disease resistance, pollination, biological control, and photosynthetic efficiency. The focus then is to enhance the crop quality through innovations in natural light growing and biostimulants, and then look at the impact on product quality through improved flavour, nutrition, and also possibly extend the shelf life and growing seasons. A great example, which we see here in the diagram, is the opportunity to start to consider building local food hubs. And here there's a potential for ripe baby cucumbers offering alternates to imported produce and leading to the potential for a national recipe box scheme. Moving a little further down the supply chain, we have another project which is called OptiBeef. And this is a carcass evaluation system utilising on-farm technologies that monitor the whole life of individual animals, such as 3D cameras, fat sensing equipment, automated weighing, and data collection to record feed intake levels. In the abattoir, the OptiBeef digital system uses the same 3D imaging and fat sensing technology to provide a more accurate and detailed measurement of carcass and the quality of the beef that's produced. By integrating both of these into a standardized system, the data which is gathered on farm and in the abattoir starts to shed light on the key factors that influence carcass yield and drive improvements in product quality and price consistency for producers and buyers. On top of that, through the data collected and the information provided, farmers are much better equipped to make informed decisions, optimize the nutrition, health, welfare, and slaughter selections they make, and also lead to a whole life monitoring of individual animals with ultimately the ability to predict yield and primal cuts. If I move on now to another example, we have a crop storage facility. And in this facility, we're looking at the impact of food quality through extended storage. These are controlled storage facilities, looking at controlling temperature and humidity to optimize the storage parameters and have crops in the best possible condition that they can be. It also includes in situ application of chemicals, which can be used to match current practices and look at improving or reducing the use of chemicals in the future. So by understanding the mechanism of quality reduction, whether it's through disease, spoilage, it's now possible to improve crop storage and reduce chemical protectants that are used during the storage procedure. Also attached to this facility is a kitchen, which can look at the quality and the performance of the final product. A great example of this is if we look at potatoes and maximize the storage potential for potatoes, we can also make the crisps from these and start to examine the impact of the storage on the final performance, taste, and texture of the crisps that are produced, leading to a better experience for the final consumers. Moving further down the supply chain, we have AgriPlas, which is exploiting the potential of cold plasma to reduce chemical risks through the supply chain. Cold plasma has extraordinary antimicrobial properties and opens up lots of interesting commercial applications. Its primary focus is in antimicrobial applications, such as replacing standard approaches to reducing bacterial load or toxins on raw products at harvest, final products, or even feedstuffs. It also can address chemical risks, allergens, bacterial toxins, and fungal toxins or mycotoxins throughout the supply chain. It also has a secondary focus, and this is supporting vet treatments by controlling infections on farms through treating the animals themselves. It's also able to increase hygiene and shelf life on food products. So by treating food products prior to packaging and removing any bacterial loads on them, it's possible to extend shelf life. And then finally, pre-treating grains to improve crop yields. A great example of this is that we've been looking at the reduction of mycotoxins on grain following plasma treatment, and then on the subsequent increases in growth when the final grains are used. Also within Queen's, we have the ACIT Lab, which is within the Institute for Global Food Security in Ireland, and is using the state-of-the-art technology to rapidly diagnose food contamination and therefore rubber stamp the safety and authenticity of foodstuffs and animal feed. ACIT provides leading platforms for both bench scale and in-field identification of food contamination and adulteration, and is now recognised as a centre of expertise by DEFRA's Food Authenticity Network. A great example of a leading capability here is iKnife technology. Here we extract vapour produced when cutting food and can instantly analyse it by rapid evaporative ionisation mass spectrometry, and this gives a unique molecular fingerprint which can identify any unexpected materials and provide further authenticity of foodstuffs. Starting to bring all of this together is a programme which is running now called the BLINK programme. And this is developing traceability within the beef supply chain using rapid DNA fingerprinting. Its goal is to develop a modern traceability and authenticity tool for the European beef industry by enabling consumers to be able to verify the origin of purchased beef. The way that this works is, given a beef supplier, they sample the genotypes of all the cattle that they produce at time of slaughter. The genotype then provides a unique barcode for each cattle. This information is then stored in a database, in addition to all other provenance information, such as ear tag ID, meat quality, health history, etc., etc. The final feedback and identification is then done by genotyping a small piece of the purchased product and searching the BLINK database by the unique DNA barcode. This therefore links it back to the original animal on all of its history, providing provenance and supporting food fraud. Finally, I thought I would cover what we think is the first mobile unit of its kind, a mobile sensory lab. This is a mobile kitchen, meat analysis equipment, and 12 sensory booths, demonstrating consumer understanding of chemical and sensory attributes and fully exploring the complex links to meat quality and provenance. The lab can be used for any type of food product and allows consumers to indicate their preference via electronic touchscreens, facilitating large data studies to be collated and analysed very quickly and very efficiently. Whilst the lab can be used to gather information on public's taste preferences, its overall aim is still to improve the quality of the food that we consume. The benefit, therefore, is learning the taste preferences of the public. People of different ages, from different places, with different backgrounds. This gives a real valuable insight and helps us improve not only the genetics of our farm animals or the growth of our crops, and lets us ensure that the consumer gets the products they want with the consistency and the quality that they expect. So this has been just a snapshot, or a taster if you like, of some of the areas being worked on across the 4 centres. Near real-time data and transparency are really the key enablers for future innovations to ensure the consumer needs are addressed and we maintain provenance and quality across our full supply chain. The combined centres, therefore, are really offering the front door for industry to world-leading expertise and capabilities. And I encourage you to talk to the centres for any future projects, collaborations, and new innovations. And we hope to talk to you all in the near future. Thank you.
Stuart Blythe from CL. Now we're going to take a short 15-minute break, and after that we will be back with the Q&A. If you want to ask a question, it's not too late, just use the question area at the bottom of this screen. And please be back here in 15 minutes.